You have never once in your life seen the world as it actually is. Not because your eyes are broken, not because you are dreaming, but because the world, at its most fundamental level, does not appear to have a definite state until something forces it to choose. This is not philosophy. This is the single most successful scientific theory ever constructed, quantum mechanics, and buried inside it is a question that has gone unanswered for nearly a century. It is called the measurement problem, and it asks something so simple that it sounds almost childish. If a particle can exist in two states at the same time, and if the math says nothing ever forces it to pick one, then why do you always see a single outcome when you look? Every interpretation of quantum mechanics is, at its core, an attempt to answer this one question, and every answer leads to the same dark corridor. The possibility that an objective, observer-independent reality, the kind you feel beneath your feet right now, may not exist at all. I want you to consider a question so basic it almost feels insulting. When you look at something, what happens? You open your eyes, light enters your pupils, your brain assembles an image, and you see a chair, a wall, a coffee cup. The object was there before you looked. It will be there after you look away. Your act of seeing did not create the chair. It did not summon the wall into existence. You simply observed what was already real. This is how the world works. This is what every human being who has ever lived has believed instinctively from the moment they were old enough to reach for a toy. The world is there. You are here. And looking at it does not change it. This assumption is so deeply embedded in your thinking that you have probably never even noticed it. It is like asking a fish to notice water. It surrounds every thought you have, every plan you make, every memory you trust. The cup was on the table before you entered the kitchen. The moon was in the sky before you stepped outside. Reality does not wait for your attention. It does not need your permission. It simply exists. And for centuries, physics backed you up. Newton described a universe of objects moving through space under the influence of forces. Those objects had definite positions, definite velocities, definite properties at every single instant. If you were not there to see the apple fall, it still fell. If no one was watching the planets orbit, they still orbited. The universe was a machine, a grand clockwork mechanism ticking along whether or not anyone was paying attention. This picture of reality is called classical realism. It has two pillars. First, objects have definite properties at all times, whether or not anyone measures them. The apple has a position. The electron has a speed. The moon is there even when you close your eyes. Second, those properties exist independently of any observer. The universe does not care that you are looking. It does not adjust itself based on your curiosity. You are a spectator at a football match. The game plays on with or without you in the stands. This worldview felt like bedrock. It felt permanent. And then, in the early 20th century, physicists walked into a laboratory and watched it crack. The crack did not come from a dramatic explosion or a failed experiment. It came from a quiet, almost humble discovery. When scientists began probing the behavior of very small things, atoms, electrons, photons, they found that the rules changed. Not slightly. Not in some manageable way that could be patched with a footnote. The rules changed so completely that they seemed to belong to a different universe. At the scale of atoms, objects did not behave like tiny billiard balls following predictable paths. They behaved like something no one had ever seen before. They behaved like possibilities. This is where most people expect to hear the story of the double-slit experiment. The famous demonstration where a single particle seems to pass through two openings at once. And yes, that experiment is important. But we are not here to retell that story for the 1000th time. We are here because of what that experiment and dozens like it forced physicists to confront. A question that cuts deeper than any specific experiment. A question that remains unanswered to this day. It is called the measurement problem. And understanding it requires that we look not at the experiments themselves, but at the mathematical machinery that describes them. Because the real crisis is not in the laboratory, it is in the equations. In 1926, an Austrian physicist named Erwin Schrödinger wrote down an equation that would become the backbone of quantum mechanics. The Schrödinger equation describes how quantum systems evolve over time. It is, in a sense, the quantum equivalent of Newton's laws. But it describes something radically different from anything Newton ever imagined. It does not track the position of a particle the way Newton tracks the trajectory of a cannonball. Instead, it tracks something called the wave function. The wave function is a mathematical object, a complex valued function that encodes everything there is to know about a quantum system. If you have a single electron, the wave function assigns a number, technically a complex amplitude, to every possible location that electron could occupy. These numbers are not positions. They are not even probabilities, at least not directly. They are amplitudes. And when you square them, you get probabilities. So the wave function does not say, the electron is here. It says, if you were to measure the electron's position, here is the probability you would find it at each possible location. The electron does not have a single definite position. It has a cloud of potential positions, weighted by the amplitudes in the wave function. Now here is the critical feature. The Schrödinger equation is completely deterministic. If you know the wave function at one moment, you can calculate exactly what the wave function will be at any future moment. There is no randomness in the equation itself. The wave function flows forward in time like a river following its course. It does not jump. It does not stutter. It evolves smoothly, continuously, predictably. This smooth evolution has a technical name. It is called unitary evolution. And it has a property that is absolutely essential to the problem we're about to face. Unitary evolution preserves superposition. Superposition is the feature of quantum mechanics that makes it fundamentally different from classical physics. If an electron can be in state A and it can be in state B, then according to the Schrödinger equation, it can also be in a state that is a combination of both. Not A or B. Not A and then B, but A and B simultaneously, blended together in a weighted mixture. This is not a statement about our ignorance. It is not like flipping a coin under a cup where the coin is definitely heads or tails and we just do not know which. The superposition is real. The electron genuinely occupies a state that includes both possibilities at once. The mathematics is explicit about this. The wave function is a sum of terms, and each term represents a different possible outcome. Until something happens to single out one of those terms, the superposition persists. And here is where the Schrödinger equation becomes both beautiful and terrifying. Because the equation is linear, superpositions never go away on their own. If the electron starts in a superposition of A and B, the equation says it stays in a superposition. It might evolve into a superposition of C and D, or some other combination, but it never collapses down to just one option. The math does not contain a mechanism for that. There is no term in the equation that says, and now, at this moment, the system chooses. The river never forks into a single stream. It just keeps spreading. So far, this is clean and elegant. The Schrödinger equation gives us a perfectly deterministic description of how quantum systems change over time. It tells us the superpositions are real and that they persist. It is one of the most precisely tested equations in the history of science. The broader framework of quantum mechanics has been confirmed to more than 12 decimal places in certain predictions, particularly in quantum electrodynamics. By every empirical measure, it works. But now we arrive at the edge of the cliff. Because when you actually go into a laboratory and measure a quantum system, something happens that the Schrödinger equation does not describe. Something it does not predict. Something it seemingly forbids. You measure the electron's position, and you get a single answer. Not a smeared cloud, not a superposition of possibilities, a specific, definite location. The electron is here, period. The measurement produces a definite outcome. Every single time, no one has ever looked at a detector and seen a blur of multiple results coexisting. No one has ever observed an electron being in two places at once. When you look, you get one answer. The superposition, the thing the equation says is real, the thing the math says should persist, vanishes. In its place, you find a crisp, concrete, classical fact. This is the measurement problem. It is the collision between two truths that should not be able to coexist. On one side, the Schrödinger equation says superpositions are real and never spontaneously disappear. On the other side, every experiment ever conducted says that measurements always produce single, definite results. Something is bridging the gap between the quantum world of superposed possibilities and the classical world of definite outcomes, and no one knows what it is. Let us make sure the sharpness of this problem is not lost. This is not a case of the theory being slightly off. This is not a rounding error. This is a case where the fundamental equation of quantum mechanics, the equation that governs everything, does not contain the mechanism that produces the one thing we always observe. It is as if you had a complete and perfect set of blueprints for a building. Every wall, every beam, every wire. And when you looked at the finished structure, there was an entire flaw that appeared in the building but was nowhere in the blueprints. That flaw is the definite outcome you see every time you open your eyes. And the blueprints, the Schrödinger equation, have no explanation for it. The historical response to this problem was swift and pragmatic. In the late 1920s, a group of physicists centered around Niels Bohr in Copenhagen crafted what became the standard way of doing quantum mechanics. Their approach involved a simple but radical move. They added a second rule. The first rule is the Schrödinger equation. It governs how the system evolves when you are not measuring it. The second rule is called the projection postulate, or sometimes the collapse postulate. It says that when a measurement occurs, the wave function instantaneously and discontinuously jumps from a superposition of many possibilities into a single definite state. The probability of landing on any particular state is given by the square of the corresponding amplitude in the wave function. This is the Born rule, named after Max Born, and it gives us the statistical predictions that match experiments so beautifully. So now you have two rules. Rule 1, smooth deterministic evolution between measurements. Rule 2, sudden probabilistic collapse during measurements. Together they form the textbook version of quantum mechanics. And they work. They allow physicists to make predictions that are confirmed in laboratory after laboratory. The standard formalism of quantum mechanics is, by any practical measure, an astonishing success. But there is a deep and ugly problem hiding inside this success. The two rules contradict each other. Rule 1 says evolution is smooth and continuous. Rule 2 says evolution is sudden and discontinuous. Rule 1 says the future is determined by the present state. Rule 2 says the outcome is fundamentally random. Rule 1 preserves superpositions. Rule 2 destroys them. These are not two aspects of the same law. They are two completely different laws patched together with duct tape. And the patch is held in place by a single word that has never been given a rigorous definition within the theory itself. That word is measurement. Think about what this means. The entire framework of quantum mechanics depends on a concept it has never made precise. When does a measurement happen? What counts as a measurement? Is it the detector that measures? Is it the computer that records the data? Is it the human being who reads the screen? The theory does not say. It draws a line between the quantum world, where superpositions exist, and the classical world, where definite outcomes live, and it calls that line measurement. But it never tells you where the line is. This was recognized almost immediately. John von Neumann, one of the most brilliant mathematicians of the 20th century, formalized quantum mechanics in the early 1930s and explicitly identified this problem. He traced what happens when a quantum system interacts with a measuring device, and then the device interacts with a recorder, and the recorder interacts with an observer. At every link in this chain, the Schrödinger equation says the superposition does not collapse. It spreads. The detector joins the superposition. The computer joins the superposition. Even the physicist's brain, which is made of atoms, joins the superposition. Von Neumann could find no point within the physical world where the chain terminates. We will walk through this chain in full detail shortly, because its logic is airtight and its implications are devastating. Von Neumann's own formalism placed what he called an abstract ego at the end of the measurement chain. Whether he intended this as a literal claim about consciousness or merely as a formal device remains debated among historians. But the implication was clear to those who followed him, particularly Wigner. The greatest mathematician to formalize quantum theory could not find a physical mechanism for collapse within the theory itself. That should tell you something about the depth of the problem. And the problem has not gone away. It has not been quietly solved in some obscure journal that the public never heard about. In 2011, a survey of physicists at a Quantum Foundations conference in Austria found no consensus on the measurement problem, with deep disagreement about whether it had been solved or even correctly formulated. Subsequent polls have consistently confirmed this divide. Nearly a century after the birth of quantum theory, the people who understand it best still do not agree on what happens when you measure a particle. Nearly a century after the birth of quantum theory, the people who understand it best still do not agree on what happens when you measure a particle. Let us take a step back and ask why this matters. You might be thinking, who cares? The theory works. Physicists can calculate the energy levels of hydrogen to 12 decimal places. They can design semiconductors and lasers. They can predict the outcomes of particle collisions at the Large Hadron Collider. If the math gives the right answers, why does it matter that the foundation has a crack in it? It matters because the crack is not in the predictions. It is in the picture of reality. Quantum mechanics tells you what you will observe, but it does not tell you what is happening when you are not observing. It does not tell you what an electron is doing between measurements. It does not tell you whether the electron has a position before you look. It does not tell you whether the moon is there when nobody's watching. And these are not abstract philosophical musings. These are questions about the nature of existence. They are questions about whether the physical world has definite properties independent of observation, or whether something far stranger is going on. Consider this. Every time you look at your hand, you see 5 fingers in specific positions. That seems like a brute fact about the world. But quantum mechanics, taken at face value, says that the particles making up your hand were in superpositions of many different configurations just moments before you looked. The act of observation, whatever that means, produced the specific arrangement you see. If you had not looked, the theory does not say your hand would have been in that same configuration. It says your hand would have been in a superposition of many configurations. This is not a failure of the theory. This is what the theory says. And the theory is the most precisely confirmed framework in all of science. So when you ask what the measurement problem is, the answer is this. It is the question of how and why the smooth, deterministic, superposition-preserving evolution described by the Schrödinger equation gives way to the sharp, random, definite outcomes we observe every time we open our eyes. It is the question of where the quantum world ends and the classical world begins. It is the question of what happens at the boundary. And it is a question that, as of today, does not have a universally accepted answer. This is not a gap in our knowledge, the way dark matter is a gap. Dark matter is a puzzle about what is out there. The measurement problem is a puzzle about the internal consistency of our most fundamental theory. It is a crack that runs through the floor of physics. And everything built on top of that floor, every prediction, every technology, every claim about the nature of matter, stands on the assumption that the crack will eventually be repaired, But after nearly 100 years of effort by some of the most brilliant minds in human history, the crack remains open. And here is the part that should unsettle you. The measurement problem is not just about electrons and photons in a laboratory. It is about the world you see when you wake up in the morning. It is about the chair beneath you, the air you breathe, the face of the person you love. All of these things are made of quantum particles. All of these things are, at the fundamental level, governed by the Schrödinger equation. And the Schrödinger equation says they should exist in vast, tangled superpositions. The fact that they do not, the fact that you see a single definite world every time you open your eyes, is the miracle that physics cannot explain. Every definite thing you have ever experienced is evidence of the measurement problem. Every solid object, every sharp sound, every clear image is a reminder that something is happening at the boundary between possibilities and facts, and we do not know what it is. You are living proof of the deepest unsolved problem in physics, and you did not even know it until now. So, the next time someone tells you that quantum mechanics is just about tiny particles in a lab, that it does not affect the real world, remember this: the real world is the problem. The real world, with its definite objects and concrete facts, is exactly what quantum mechanics cannot explain. The theory describes a universe of overlapping possibilities, and yet you live in a world of sharp outcomes. That gap between the possibilities and the outcomes is the measurement problem. And it has been staring at physics for almost 100 years, waiting for someone to blink. No one has blinked yet, but the gap has not closed either. And the longer it stays open, the darker the implications become. Because if we cannot explain how definite outcomes emerge, then maybe the definite world we think we live in is not as definite as we believe. Maybe the sharp edges are softer than they look. Maybe the concrete facts are less concrete than they feel. And maybe, just maybe, the world only looks real because we are looking at it. That is the crack in the foundation, and it goes all the way down. Now that we understand the shape of the problem, we need to get inside the machinery and see exactly where it breaks. Because the measurement problem is not a vague philosophical complaint about the meaning of reality. It is a precise, technical contradiction embedded in the mathematical framework of quantum mechanics. And to feel the full weight of that contradiction, we need to understand what the theory actually says when you write it down. Not the pop science version, not the metaphor, the actual structure. Because when you see the gears up close, you realize they are grinding against each other. And they have been grinding since the day the theory was born. Let us start with the object at the center of everything, the wave function. Earlier we described it as a mathematical object that encodes probabilities. That is true, but it undersells what is really going on. The wave function is not a list of odds like a bookmaker's sheet. It is a living, breathing mathematical entity that evolves through an abstract space. And that space is not the three-dimensional room you are sitting in. It is something called Hilbert space. Hilbert space is a mathematical arena with potentially infinite dimensions. Each dimension corresponds to a possible state the system could be in. For a single particle that can be in position A or position B, the Hilbert space is two-dimensional. The wave function is a vector, an arrow pointing somewhere in that space. If the arrow points entirely along the A-axis, the particle is definitely in position A. If it points entirely along the B-axis, the particle is definitely in position B. But here is the key feature. The arrow can point in any direction, including directions that are between A and B. When the arrow is tilted, pointing partly toward A and partly toward B, the particle is in a superposition. It is not in A. It is not in B. It is in a state that has no classical analog, a state that contains both possibilities simultaneously, weighted by the components of the arrow along each axis. This is not a metaphor. The arrow is the most complete description of reality that quantum mechanics provides. There is nothing hidden behind it. There is no secret file that says the particle is really in A, and we just do not know it. The arrow pointing between A and B is the full truth. The theory is explicit about this, and the relative lengths of the arrow's components along each axis determine the probabilities. If the arrow is tilted mostly toward A, there is a high probability of finding the particle in A when you measure it. If it is tilted mostly toward B, the probability shifts accordingly. The famous Born rule gives you these probabilities by squaring the components. Now, the Schrödinger equation tells us how this arrow moves through Hilbert space over time. And the motion is elegant. The arrow rotates smoothly. It never jumps. It never stutters. It traces a continuous path through the abstract space. And that path is entirely determined by the system's energy. If you know where the arrow is pointing right now, the equation tells you exactly where it will point at any future time. This is unitary evolution, and it has a property that is mathematically ironclad. It preserves the length of the arrow. The total probability, the sum of all possible outcomes, always adds up to 1. Nothing is created. Nothing is destroyed. Possibilities redistribute, but the total remains constant. The equation is a perfect, lossless machine, and crucially, this machine is linear. Linearity is a mathematical property that sounds technical, but has a devastating consequence for the measurement problem. It means that if the equation can produce state A as a valid evolution, and it can produce state B as a valid evolution, then it can also produce any combination of A and B as a valid evolution. Superpositions do not decay. They do not fade. They do not spontaneously resolve into one option or the other. The linearity of the Schrödinger equation mathematically guarantees that once a system is in a superposition, it stays in a superposition. The equation has no built-in exit door. Let that really land. This is not a limitation of our current understanding. This is not a case where physicists have not yet found the right correction term. The Schrödinger equation has been tested to extraordinary precision. Every experiment ever conducted confirms that quantum systems evolve exactly as the equation predicts, smoothly, linearly, and unitarily. There is no evidence that the equation ever fails, and yet every measurement ever conducted produces a single definite result. Something that the equation, in its pristine and perfect form, says should never happen. This is the crack, not a hairline fracture, a canyon, and the standard formalism of quantum mechanics bridges this canyon with something that, when you look at it honestly, is an act of intellectual violence. It bridges it with the projection postulate. The projection postulate, sometimes called the collapse postulate or von Neumann's process 1, is the second rule of quantum mechanics, and it is nothing like the first rule. It says that when a measurement is performed on a quantum system, the wave function does not continue its smooth rotation through Hilbert space. Instead, it instantaneously and discontinuously snaps to one of the possible outcomes. The arrow, which was pointing between A and B, suddenly jumps to point entirely along A or entirely along B. The superposition is destroyed. The other possibilities vanish. A single result is selected. And the probability of each result is given by the Born rule. This collapse is not smooth. It is not continuous. It is not deterministic. It violates every property of the Schrödinger equation. The first rule says evolution is continuous, and the second rule says it is discontinuous. The first rule says evolution is deterministic, and the second rule says it is probabilistic. The first rule says superpositions persist, and the second rule says they are annihilated. These are not two complementary aspects of a unified theory. They are two flatly contradictory rules jammed together in the same textbook and separated by nothing more than the word measurement. This would be acceptable if the word measurement had a clear, rigorous, physical definition. If we could say a measurement occurs when the system interacts with an apparatus that satisfies conditions X, Y, and Z, then we would have a clean theory. We would know exactly when to apply Rule 1 and when to apply Rule 2. The transition would be sharp, unambiguous, and physically grounded. But no such definition exists. The theory does not tell you what a measurement is. It does not specify the physical criteria that, not say, when an electron hits a rock on not say, when an electron hits a rock on the surface of Mars, is that a measurement? The math does not say. When an electron interacts with a silicon detector in a physics lab, is that a measurement? The math still does not say, at least not from first principles. The only reason we apply the collapse postulate in the lab is because we, the human users of the theory, have decided that this particular interaction counts. We drew the line, not the physics. This arbitrary line has a name. It is called the Heisenberg cut. It is the imaginary boundary between the quantum world, where superpositions exist and the Schrödinger equation rules, and the classical world, where definite outcomes exist and the collapse postulate applies. Everything on the quantum side of the cut is described by smooth evolution. Everything on the classical side is described by sharp collapse. And the placement of the cut is entirely up to us. Niels Bohr, the architect of the Copenhagen interpretation, was remarkably candid about this. He insisted that the measuring apparatus must be described in classical terms. He said that quantum mechanics only makes predictions relative to a classical framework. The theory, in his view, does not describe reality directly. It describes the results of experiments performed with classical instruments. The cut between quantum and classical is not a physical boundary. It is a pragmatic choice made by the experimenter. And in practice, this works brilliantly. Physicists place the cut wherever it is convenient, calculate the probabilities, compare them to experimental results, and collect their Nobel Prizes. The theory is a prediction machine of extraordinary power. But a prediction machine is not a description of reality. It is a recipe. And the measurement problem is the question of what is actually happening in the kitchen. To see why this question is so difficult, let us return to the von Neumann chain and follow it more carefully than we did before. Because the chain does not just illustrate the problem. It proves, with mathematical rigor, that the problem cannot be solved by moving the Heisenberg cut to any specific location within the physical world. Consider the simplest possible quantum measurement. An electron is in a superposition of spin up and spin down. It enters a Stern-Gerlach apparatus, a device that deflects spin-up particles upward and spin-down particles downward. The electron hits a detector. The detector registers a result. Now, where does the collapse happen? Let us try every option. Option 1. The collapse happens at the Stern-Gerlach magnet, the moment the electron's path is deflected. But the magnet is a physical system made of atoms. If we apply the Schrödinger equation to the electron plus the magnet, linearity demands that the combined system enters a superposition. One branch has the electron deflected up and the magnet in a slightly different state. The other branch has the electron deflected down and the magnet in another slightly different state. No collapse. The superposition has simply spread from the electron to the electron-magnet system. Option 2. The collapse happens at the detector. The electron hits a fluorescent screen and produces a flash of light. Surely this macroscopic event constitutes a measurement. But the screen is made of atoms. The flash is made of photons. Apply the Schrödinger equation to the electron, plus the magnet plus the screen, and you get a superposition of screen flashed at the top and screen flashed at the bottom. The superposition has spread again. It has infected the screen, incorporating it into the entangled whole. Option 3. The collapse happens when the photons from the flash travel to a camera and produce a digital image. But the camera is a physical system. Its pixels are made of silicon atoms. Its circuits are made of copper and doped semiconductor. Apply the equation, and the camera enters the superposition. Camera displays up and camera displays down coexist. Option 4. The collapse happens when the signal travels through a cable to a computer monitor. But the monitor is atoms. Apply the equation, and the monitor enters the superposition. Option 5. The collapse happens when photons from the monitor enter the physicist's eye and stimulate the retina. But the retina is made of cells. Cells are made of molecules. Molecules are made of atoms. Apply the equation. The retina enters the superposition. Option 6. The collapse happens when the neural signal travels from the retina to the visual cortex of the brain. But neurons are made of atoms. Synapses are chemical processes. Apply the equation. The brain enters the superposition. This is the von Neumann chain, and it is not a thought experiment. It is a mathematical proof. At every link of the chain, the system is physical, made of quantum particles, and the Schrödinger equation applies. At every link, linearity guarantees that the superposition does not collapse, but spreads. There is no natural stopping point. There is no link in the chain where the physics suddenly changes. The equation treats every atom the same, whether that atom is part of an electron beam or part of a human brain. Von Neumann followed this chain to its logical conclusion and found that within the physical formalism of quantum mechanics, there is no place to put the collapse. If you insist that the collapse is a real physical process, you have to identify the point at which the Schrödinger equation stops working. And no one has ever identified that point. No experiment has ever found a scale, a mass, a complexity threshold, or any other physical criterion at which quantum behavior gives way to classical behavior. This is not for lack of trying. Over the past several decades, extraordinary experiments have demonstrated quantum behavior in larger and larger systems. In 2019, a team in Vienna demonstrated quantum interference with molecules containing over 2,000 atoms. That is a single object, far larger than anything the founders of quantum mechanics ever imagined behaving quantum mechanically. Superconducting circuits in modern quantum computers maintain superpositions involving billions of electrons acting collectively. The boundary between quantum and classical keeps retreating, always just out of reach, always further than anyone expected. Some physicists hoped that gravity would provide the cut, that at some mass scale, the gravitational self-energy of an object would become large enough to trigger an objective collapse. Roger Penrose has proposed this, and we will examine it in detail later. But as of today, no gravitational collapse mechanism has been experimentally confirmed. The Heisenberg cut remains unfixed. The boundary between the quantum world and the classical world has never been found because it may not exist. Now, let us confront what this means for the structure of the theory. Quantum mechanics, as it is taught in textbooks and used in laboratories around the world, is not a single coherent theory. It is two theories duct taped together. Theory 1 is the Schrödinger equation. It is deterministic, continuous, linear, and universal. It applies to all physical systems at all times. Theory 2 is the projection postulate. It is probabilistic, discontinuous, nonlinear, and applied only during measurements. These two theories are not derived from each other. They are not different limits of a deeper law. They are independent postulates that flatly contradict each other, connected only by the undefined word measurement. This situation is unique in the history of science. No other fundamental theory has this structure. General relativity does not have two incompatible rules. The standard model of particle physics does not switch between contradictory equations depending on whether a human is watching. Only quantum mechanics requires this bizarre dualism. And the fact that it works, that this patchwork framework produces predictions of breathtaking accuracy, makes the problem more disturbing, not less. It means that the duct tape is strong. It means the contradiction is deep. It means that we are getting the right answers from a framework that does not make internal sense. Imagine that you are an engineer and someone hands you the blueprints for a bridge. The first page says the bridge is made of steel beams connected by rigid bolts. The second page says the bridge is made of rubber cables connected by magnets. Both pages produce the correct load-bearing predictions. The bridge stands. Cars drive across it. But the blueprints are incoherent. They describe two different bridges. You would not say the problem is solved just because the bridge is standing. You would say, there is a serious gap in your understanding of why the bridge stands. That is the measurement problem. The bridge of quantum mechanics is standing, but the blueprints are broken. And the consequences of this brokenness are not confined to the philosophy seminar. They ripple outward into every attempt to extend quantum mechanics to new domains. When physicists try to apply quantum theory to the entire universe, as in quantum cosmology, the measurement problem becomes a roadblock. Who is measuring the universe? There is no external observer. There is no classical apparatus outside the system. The Heisenberg cut cannot be drawn because there is nothing on the other side of it. The projection postulate has nowhere to live. When physicists try to unify quantum mechanics with general relativity, the measurement problem lurks in the background. Any theory of quantum gravity must account for the superposition of space-time itself. But if space-time can be in a superposition, then the classical framework that Bohr insisted we need for measurement does not exist at the fundamental level. The scaffolding dissolves. When physicists try to build quantum computers, the measurement problem is not an abstraction. It is an engineering constraint. The entire challenge of quantum computing is to maintain superpositions long enough to perform calculations. Every interaction with the environment threatens to cause the wave function to behave as if it has collapsed. Understanding exactly when and how superpositions are destroyed is not a philosophical luxury. It is the difference between a working quantum computer and a very expensive paperweight. The measurement problem is not a footnote. It is not a historical curiosity. It is an open wound at the heart of modern physics. It tells us that our most fundamental theory contains a flaw so deep that the theory cannot even describe, in a self-consistent way, the process by which it is tested. The very act of checking the theory breaks the theory. Some physicists will tell you this is fine. They will tell you that physics is about predictions, not about reality. That the job of a theory is to tell you what numbers will appear on your instruments, and quantum mechanics does that better than any theory before it. They will tell you the measurement problem is a pseudo-problem, a confusion born from demanding that physics tell a story about what is really happening, when the theory only promises probabilities. But this pragmatic shield has a flaw. If you do not know what is really happening, you do not know the limits of your theory. You do not know when it will break. You do not know how to extend it. And you do not know whether the beautiful predictions you are making today are artifacts of a framework that works for the wrong reasons. Ptolemy's geocentric model of the solar system made excellent predictions for over 1,000 years. It put the Earth at the center and used intricate circles upon circles to match the motions of the planets. It worked. But it was wrong. The predictions were right, but the picture of reality was fundamentally mistaken. And the only way to move beyond Ptolemy was to demand a theory that did not just predict, but explained. That did not just match the data, but made sense. The measurement problem is the demand that quantum mechanics make sense, not just as a recipe for generating probabilities, but as a coherent description of the physical world. What is actually happening between measurements? Does the electron have a position when you are not looking? Is the wave function a real physical object or just a bookkeeping device? Does collapse actually occur, and if so, what triggers it? These questions are not idle speculation. They are the fault lines along which the next revolution in physics will split the Earth. Every proposed solution to the measurement problem leads to a radically different picture of reality. One solution says the universe splits every time a measurement is made. Another says hidden variables guide particles along definite paths. Another says the wave function physically and spontaneously collapses at random intervals. And yet, another says there is no objective reality at all, only relationships between observers and systems. These are not minor variations. They are completely different ontologies, completely different answers to the question of what the world is made of. And the fact that the measurement problem remains unsolved means that we genuinely do not know which of these pictures is correct. We do not know what the world is. We do not know what exists between measurements. We do not know whether the chair you are sitting in has a definite state right now, or whether it is an astronomically complex superposition that merely appears definite because you are entangled with it in a way that masks the branches. The textbook tells you to shut up and calculate, and for decades that was enough. But the cracks are spreading. The experiments are getting more precise, the contradictions are getting harder to ignore, and the question at the center of it all, the question the textbook cannot answer, is the same question it has always been. If the Schrödinger equation is right, and superpositions never collapse on their own, then why do you see a definite world every time you open your eyes? The rules are breaking themselves, and no one knows how to make them stop. We have seen the wound. We have traced its edges. We know that quantum mechanics contains two incompatible rules, and that the word holding them together, measurement, has no definition within the theory. Now comes the natural question. What do we do about it? How do we fix this? How do we save our deepest theory of nature from its own internal contradiction? The answer is that physicists have tried. Since the founding generation of quantum theory, some of the greatest minds in the history of science have stared at the measurement problem and proposed solutions. These solutions are called interpretations of quantum mechanics, and each one is a different way of answering the same question. What is actually happening when a quantum system is measured? But here's the part that most people never hear. None of these interpretations has won. None has been experimentally confirmed over the others. They all reproduce the same predictions. They all match the data equally well, and they all describe completely different realities. This means that the choice between them is not, at present, an empirical question. It is a question about what you are willing to sacrifice, because every interpretation saves the math by giving up something else, something you might not want to lose. Let us walk through the four major contenders, not as a textbook survey, but as a tour of the prices physicists are willing to pay to keep reality from collapsing under its own contradictions. The first and oldest response to the measurement problem is the Copenhagen interpretation. It is the one most physicists learn first. It is the one most textbooks teach. And it is, in many ways, the most honest response to the problem, precisely because it refuses to answer it. The Copenhagen interpretation was developed primarily by Niels Bohr and Werner Heisenberg in the late 1920s. Its core claim is simple and, on the surface, modest. Quantum mechanics is a tool for predicting the outcomes of experiments. It is not a description of an underlying reality. The wave function is not a physical object floating through space. It is a mathematical device that encodes our knowledge about a system. When we perform a measurement, the wave function updates to reflect the new information we have gained. That is all. In the Copenhagen view, asking what the electron is doing between measurements is like asking what a word means when nobody is reading it. The question is not wrong. It is empty. Quantum mechanics does not describe the world between observations. It describes the connections between observations. To demand a story about what happens in the gaps is to misunderstand what the theory is offering. This sounds clean. It sounds disciplined. And for practical purposes, it works beautifully. You set up your experiment. You apply the Schrödinger equation. You use the Born rule to calculate probabilities. You compare with data. You move on with your life. But there is something deeply strange about this position when you look at it closely. The Copenhagen interpretation is the only major framework in all of physics that explicitly tells you not to ask what is real. Every other theory, from Newton's mechanics to Einstein's relativity to the standard model of particle physics, offers a picture of the world. Newton says there are particles moving through space under the influence of forces. Einstein says space-time is a curved manifold shaped by matter and energy. The standard model says there are quantum fields, whose excitations manifest as particles. These theories all claim that something exists. They have an ontology. They tell you what the furniture of the universe looks like. Copenhagen strips that away, It says the furniture is none of your business. You can talk about the readings on your instruments. You can talk about the statistics of your results. But you cannot ask what is behind the curtain. There might not be a curtain. There might not be a behind. For Bohr, this was not a failure of imagination. It was a feature. He believed that human concepts like position, momentum, and trajectory were borrowed from everyday experience and simply did not apply to the quantum world. Trying to picture what an electron is doing between measurements was, in his view, like trying to picture the color of jealousy. The question assumes categories that do not fit. The quantum world is not a classical world in miniature. It is something else entirely, something that our evolved brains are not equipped to visualize. This philosophical humility has a dark side. If the theory does not describe reality between measurements, then what is the status of the collapse? Is the wave function collapse a physical event or just a change in bookkeeping? Copenhagen never clearly answers this. It hovers in an ambiguous zone between physics and epistemology, and that ambiguity has frustrated physicists for generations. It also leaves the Heisenberg cut completely in place. The boundary between the quantum world and the classical world remains undefined. The theory still relies on an external classical apparatus to anchor the concept of measurement. And as we saw with the von Neumann chain, every apparatus is made of quantum particles. If you take the formalism seriously, there is no truly classical apparatus anywhere in the universe. Copenhagen works by refusing to look at the place where the contradiction lives. It draws the curtains and says, the view is not part of the show. For decades, this was enough. But eventually a young physicist decided to open the curtains and face whatever was behind them. His name was Hugh Everett III, and his solution to the measurement problem was the most audacious proposal in the history of physics. Everett looked at the two incompatible rules of quantum mechanics and asked a simple question. What if the first rule is the only rule? What if the Schrödinger equation is the complete description of reality with no exceptions? What if we simply delete the projection postulate and let the math speak for itself? The consequence is immediate and staggering. If the Schrödinger equation never stops working, then superpositions never collapse. The electron that is in a superposition of spin up and spin down stays in a superposition after it hits the detector. The detector enters a superposition. The computer enters a superposition. The physicist enters a superposition. The entire laboratory, the entire planet, the entire universe enters a superposition of every possible outcome, of every possible interaction that has ever occurred. Everett did not flinch. He accepted this. He said the universe is exactly the vast, sprawling, branching superposition that the Schrödinger equation describes. But he added a crucial insight. He said that within this universal superposition, each branch is internally consistent. Inside the branch where the electron is spin up, the detector reads up, the computer displays up, and the physicist sees up. Inside the branch where the electron is spin down, everything reads down. The branches do not interfere with each other in practice because of a process called decoherence, which we will examine in detail later. Each branch looks, from the inside, exactly like a classical world with a single definite outcome. This is the many worlds interpretation. And it solves the measurement problem with a single clean stroke. There is no collapse. There is no projection postulate. There is no Heisenberg cut. There is no undefined concept of measurement. There is only the Schrödinger equation applied universally all the time, without exception. The appearance of collapse is an illusion created by the branching of the universal wave function. You think the electron chose spin up because you are in the branch where it is spin up. But the other branch, the one where it is spin down, is equally real. There is another version of you in that branch, equally convinced that the electron chose spin down. The mathematical elegance of this is hard to overstate. Many worlds is the only major interpretation that does not add anything to the formalism of quantum mechanics. It does not modify the Schrödinger equation. It does not add a collapse mechanism. It does not introduce hidden variables. It simply takes the existing math at face value and says, this is what the universe looks like. But the price? The price is beyond anything the human mind was designed to accept. If many worlds is correct, then every quantum interaction that has ever occurred has produced a branching of the universe. Not metaphorically, literally. Every photon absorbed by a leaf, every radioactive atom that decays, every neural firing in your brain has split the universe into multiple copies. The number of branches is not large. It is not astronomical. It is a number so far beyond astronomical that no word in any human language describes it. There are more branches of the universal wave function than there are atoms in the observable universe, by a margin so vast that the comparison itself is meaningless. In some of those branches, you stopped watching this video 5 minutes ago. In some of them, you were never born. In some of them, the dinosaurs never went extinct. In some of them, the Earth never formed. All of these branches are, according to the theory, equally real. They are all part of the same universal wave function. They are all evolving under the same Schrödinger equation. You cannot visit them. You cannot detect them. But the math says they are there. And there is a deeper concern. Many worlds reproduces the predictions of quantum mechanics only if the probabilities we observe match the Born rule. But in a universe where every outcome happens, what does probability even mean? If both spin up and spin down occur with certainty, in what sense is one outcome more probable than the other? This is called the probability problem, and it has been the subject of intense debate for decades. Proponents like David Deutsch and David Wallace have proposed sophisticated arguments based on decision theory to derive the Born rule from many worlds. Critics argue these derivations are circular. The debate continues. Many worlds is the purest interpretation. It sacrifices nothing in the formalism, but it demands that you accept an infinity of unobservable parallel realities as the price of mathematical consistency. Whether that price is too high is a question that divides physicists to this day. Now let us consider an interpretation that goes in the exact opposite direction. Instead of deleting the collapse postulate, what if we promote it? What if we say that collapse is not a pragmatic trick or a bookkeeping update, but a real, physical, objective process that happens in nature whether or not anyone is watching? This is the approach taken by objective collapse theories, the most famous of which is the GRW theory, named after Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber, who proposed it in 1986. The idea is elegant in its brute force. GRW modifies the Schrödinger equation. It adds a new term, a tiny random process that affects every particle in the universe. At random intervals, each particle has a small probability of undergoing a spontaneous localization. Its wave function, which might be spread out over a wide region, suddenly and randomly narrows to a small area. This is not caused by measurement, it is not caused by observation, it is a fundamental physical process built into the laws of nature. For a single particle, these spontaneous collapses are extraordinarily rare. The GRW theory proposes that a given particle undergoes a localization event roughly once every 100 million years. For a single electron, this is negligible. The electron behaves quantum mechanically for all practical purposes. Its wave function spreads, it interferes, it superposes. The GRW modification is invisible, but now consider a macroscopic object. A cat, for instance, contains something on the order of 10 to the power of 27 particles. Even though each individual particle collapses only once every 100 million years, there are so staggeringly many particles that at least one of them is collapsing almost continuously. And because the particles in a solid object are bound together, a collapse of one particle drags the rest along with it. The wave function of the entire cat is localized almost instantly, not by an observer, not by a measurement, by the sheer statistics of the GRW process acting on a sufficiently large collection of particles. This is the genius, of GRW. It provides a natural explanation for why microscopic systems behave quantum mechanically and macroscopic systems behave classically. The transition is not caused by a Heisenberg cut or a conscious observer. It is caused by a physical mechanism that scales with the number of particles. Small systems stay in superposition because spontaneous collapse is rare. Large systems collapse quickly because spontaneous collapse is frequent. The measurement problem is solved not by reinterpreting the formalism, but by changing the physics. But changing the physics has consequences. The GRW modification violates energy conservation, though by such a tiny amount that it has not been detected. It also produces a very slight heating of matter, because the spontaneous localization events inject a minuscule amount of energy into the system. These effects are predictions, real, testable predictions that differ from standard quantum mechanics. Experiments are currently searching for these signatures. So far, none have been found. This does not rule out GRW, because the effects are incredibly small, but it means the theory is not yet confirmed. There is also a conceptual cost. The GRW theory introduces two new fundamental constants: the rate of spontaneous collapse and the width of the localization. These constants are not derived from anything. They are free parameters, tuned by hand to match the observed behavior of the world. They have no deeper explanation. This makes the theory feel ad hoc to some physicists. It solves the measurement problem, but it does so by adding machinery that has no independent motivation. The modification works, but it feels bolted on rather than emerging from a deeper principle. Roger Penrose has proposed a different version of objective collapse, one motivated by gravity. His idea is that a quantum superposition of two different mass distributions creates a superposition of two different space-time geometries. General relativity, Penrose argues, does not allow this. The conflict between the two geometries creates an instability, and the system is forced to collapse to one configuration or the other. The timescale for this collapse depends on the gravitational self-energy of the superposition. For small systems, the energy difference is negligible and the system can stay in superposition indefinitely. For large systems, the energy difference is significant and collapse happens quickly. Penrose's proposal has the aesthetic advantage of connecting the measurement problem to gravity, potentially linking quantum mechanics to general relativity, but it too has not been experimentally confirmed. The macro satellite proposal and various ground-based experiments have been designed to test gravitational collapse, but as of today, the results are inconclusive. Objective collapse remains a promising but unproven approach. The fourth and final interpretation we will examine takes the most conservative path of all. It does not delete the collapse postulate. It does not modify the Schrödinger equation. It does not multiply universes. Instead, it adds something to the picture that quantum mechanics left out: particles with definite positions, moving along definite trajectories at all times. This is the pilot wave theory, also called Bohmian mechanics, developed by Louis de Broglie in 1927 and revived by David Bohm in 1952. In the pilot wave theory, there are two things in the world. First, there is the wave function. It evolves according to the Schrödinger equation, exactly as in standard quantum mechanics. Nothing has changed, nothing is modified. The wave function spreads out, superposes, and interferes exactly as the math dictates. But second, and this is the radical addition, there is also a particle, a real, actual, definite particle with a precise position at every moment in time. The particle does not move randomly. It is guided by the wave function. The wave function acts as a pilot wave, pushing the particle along a specific path through space. The equation that governs this motion is called the guiding equation. It takes the wave function as an input and tells the particle where to go. The particle surfs the wave, always riding one particular crest, always following one specific trajectory through the landscape of possibilities. In this picture, the measurement problem dissolves. When you measure the position of an electron, you are not collapsing a superposition. You are simply discovering where the particle was all along. The electron always had a definite position. It always followed a definite path. The wave function is still there, spread out and superposed, but the particle is localized. What you see in the laboratory, the single dot on the screen, is the actual position of an actual thing. The Born rule, the statistical distribution of outcomes, emerges naturally. Bohm showed that if you start with a collection of particles whose initial positions are distributed according to the square of the wave function, then the guiding equation guarantees they will remain distributed that way forever. The probabilities of quantum mechanics are not fundamental. They are a consequence of our ignorance about the exact initial positions of the particles, much like the probabilities in classical statistical mechanics arise from our ignorance about the exact positions and velocities of gas molecules. This is profoundly satisfying. It restores determinism. It restores particle trajectories. It restores the idea that things have definite properties at all times. The moon is there when nobody is looking. The electron went through one slit, not both. The wave function is real, but the particle is also real, and the particle is what you detect. The measurement problem is not solved by reinterpreting the math. It is dissolved by adding a physical element that the math was missing. But there is a cost, and the cost is severe. The guiding equation is non-local. When two particles are entangled, the velocity of one particle depends instantaneously on the position of the other, no matter how far apart they are. This is not a subtle, theoretical consequence. It is built into the structure of the theory at the most fundamental level. Pilot wave theory explicitly violates the principle of locality. It says that what happens here can instantaneously affect what happens on the other side of the universe. In one sense, this is not surprising. Bell's theorem proved in 1964 that any theory that reproduces the predictions of quantum mechanics must be non-local, or give up realism, or give up some other deeply held assumption. Pilot wave theory chooses to keep realism and accept non-locality. It pays the toll honestly. But the toll is steep. Non-locality creates tension with special relativity, which is built on the principle that no influence can propagate faster than light. Bohmian mechanics can be made consistent with the predictions of relativity, but its underlying dynamics are defined in a preferred reference frame. There is a universal simultaneity built into the theory that relativity says should not exist. There is also a criticism that cuts more to the aesthetics. In pilot wave theory, the wave function is a real, physical entity. It guides the particles, but after a measurement, most of the wave function becomes irrelevant to the particle. It continues to exist, spreading out through the vast emptiness of configuration space, but the particle has moved on. These empty branches of the wave function are sometimes called zombie waves. They carry no particles, they influence nothing, but they are still there, mathematically real, taking up space in the theory. Critics, particularly proponents of many worlds, point out that if you are going to accept all these branches of the wave function as real, you might as well accept that they contain real outcomes, and then you are back to many worlds without the particles. Defenders of pilot wave theory counter that there is a meaningful difference between a branch that contains a particle and a branch that does not. The particle is the thing you observe. The empty branches are mathematical residue. They are real in the formalism, but not in the laboratory. Let us now step back and look at what we have. 4 interpretations, 4 completely different pictures of reality. Copenhagen says the question of what is real between measurements has no answer. Many World says everything is real, every possible outcome occurs in a separate branch of an infinitely splitting universe. Objective collapse says the Schrödinger equation is wrong and needs a new physical mechanism. And pilot wave says particles are real and always have definite positions. But the universe is fundamentally non-local. These are not 4 variations on a theme. These are 4 different universes. In one, there is no reality between measurements. In another, there are infinite realities. In another, reality collapses spontaneously. And in the last, reality is deterministic but woven together by instantaneous connections across the cosmos. And here is the fact that should keep you up at night. We cannot currently distinguish between them. All 4 interpretations reproduce the same experimental predictions. The data does not pick a winner. The experiments do not choose. The universe, as far as we can tell, is hiding its answer behind a wall of empirical equivalence. This means that the measurement problem is not just unsolved, it is unsolvable by current methods. The question of what happens when you measure a quantum system is, at present, not an empirical question. It is a choice about what you are willing to believe, a choice about what you are willing to sacrifice. Are you willing to sacrifice the concept of reality itself? Then Copenhagen is your home. Are you willing to sacrifice uniqueness and accept an infinity of parallel selves? Then many worlds awaits. Are you willing to sacrifice the Schrödinger equation, the most precisely confirmed dynamical law we possess, and modify it with new untested mechanisms? Then objective collapse is your gamble. Are you willing to sacrifice locality and accept that the universe is woven together by faster-than-light connections? Then pilot wave theory will take you in. Each interpretation saves something. Each interpretation destroys something. And none of them has been proven right. The measurement problem sits at the center of physics like a locked door. We have 4 keys. Each one fits the lock. But each one opens onto a completely different room. And we have no way of knowing which room is real. That is the state of play. That is where the science stands. Nearly a century after the birth of quantum mechanics, the most fundamental question it raises remains unanswered. And the answers on offer are not reassuring. They are not converging on a comfortable consensus. They are diverging into increasingly radical and incompatible visions of what the universe is made of. The measurement problem was supposed to be a temporary embarrassment, a placeholder for a deeper understanding that would come along shortly. It has become something else entirely. It has become the fault line along which our understanding of reality threatens to split apart. And the deeper we dig, the wider the fault line grows. There is a word that has haunted every sentence of this journey so far. It has appeared in every argument, every interpretation, every attempt to make sense of quantum mechanics. And yet, despite being the single most important word in the entire framework, it has never been given a rigorous physical definition. That word is measurement. We have talked about what happens when you measure a quantum system. We have talked about the collapse that measurement supposedly triggers. We have talked about interpretations that try to explain measurement, replace measurement, or deny that measurement is special at all. But we have never stopped to ask the most dangerous question of all. What is a measurement? What exactly has to happen for the universe to go from a fog of possibilities to a single definite fact? Because if you pull on this thread hard enough, the entire fabric of our understanding starts to unravel. And what you find underneath is something most physicists would rather not talk about. Let us start with the obvious answer. A measurement is when a detector registers a result. An electron hits a screen and produces a flash. A Geiger counter clicks. A photon strikes a CCD sensor and generates an electrical signal. These are measurements. They produce definite, recorded outcomes. This seems straightforward, but it is not. Because a detector is a physical object. It is made of atoms. Those atoms obey the Schrödinger equation. And as we saw with the von Neumann chain, the Schrödinger equation does not produce definite outcomes. It produces superpositions. When the electron hits the screen, the equation sees the screen enters a superposition of flashed here and flashed there. The detector does not collapse the wave function. It joins the superposition. So the detector is not performing a measurement in any fundamental sense. It is just another quantum system getting entangled with the first. Fine. Maybe a measurement requires amplification. Maybe the key ingredient is that the quantum event gets magnified to a macroscopic scale. The electron triggers an avalanche of electrons in the detector. The signal gets amplified until it moves a needle or lights a pixel. Now we have a macroscopic record. Surely that counts. But amplification is just more atoms doing more quantum things. There is no point in the amplification chain where the physics suddenly changes. There is no threshold of bigness at which the Schrödinger equation hands off to classical mechanics. We have already seen that quantum behavior has been demonstrated in molecules containing thousands of atoms, in superconducting circuits involving billions of electrons. The boundary between small and big, between quantum and classical, has never been found. Amplification does not solve the problem. It just makes the superposition bigger. What about irreversibility? Maybe a measurement is defined by the fact that it leaves a permanent record. Once the detector clicks, you cannot unclick it. The information is burned into the physical world. Maybe this irreversible change is what constitutes a measurement. This is a more sophisticated idea, and it leads us toward the most important development in the foundations of quantum mechanics in the last 50 years. It leads us to decoherence. Decoherence is the process by which a quantum system loses its ability to exhibit interference effects due to interactions with its environment. It was developed in the 1970s and 80s, primarily by the German physicist Heinz-Dieter Zeh and later by Wojciech Zurek, and it has fundamentally changed how physicists think about the measurement problem. But it has also been widely misunderstood. Many physicists and science writers have claimed that decoherence solves the measurement problem. It does not. And understanding why it does not is essential to grasping the true depth of the crisis. Here is how decoherence works. Consider an electron in a superposition of spin up and spin down. In a perfectly isolated system, these two branches of the superposition can interfere with each other. They produce the characteristic interference patterns that distinguish quantum behavior from classical behavior. The superposition is coherent, meaning the phase relationships between the branches are preserved. Now, let the electron interact with its environment, not with a deliberate measuring device, but with the countless stray particles, photons, air molecules, and thermal fluctuations that fill any real physical setting. Each of these environmental particles becomes entangled with the electron. The spin-up branch of the electron becomes correlated with one state of the environment. The spin-down branch becomes correlated with a different state of the environment. As more and more environmental particles become entangled, the two branches of the superposition become encoded in orthogonal, completely distinct states of the environment. And here is the critical effect. Once the branches are correlated with different environmental states, they can no longer interfere with each other. Interference requires the branches to overlap, to be coherent. But now they are separated, not in physical space, but in the vast space of environmental correlations. For all practical purposes, the branches have become invisible to each other. The superposition has not collapsed. The wave function has not jumped. Both branches still exist in the full quantum description. But locally, from the perspective of the system alone, ignoring the environment, the system looks as if it has collapsed into one branch or the other. The off-diagonal terms in the density matrix, the mathematical elements that encode the interference between branches, decay to zero with extraordinary speed. For a macroscopic object at room temperature, this happens in a timescale so short it makes a femtosecond look like a geological epoch. We are talking about timescales on the order of 10 to the power of minus 40 seconds. Decoherence is fast. It is devastatingly, incomprehensibly fast. This explains why we never see macroscopic superpositions. The reason you do not see your coffee cup in two places at once is not that the cup is too big for quantum mechanics. It is that the cup is interacting with trillions upon trillions of air molecules and photons every fraction of a second. Each interaction entangles the cup with its environment, spreading the superposition into the environmental degrees of freedom. Within an unimaginably tiny window of time, the interference terms are suppressed. The cup behaves classically. It appears to be in one place, and this happens automatically without any need for a conscious observer, a Heisenberg cut, or a collapse postulate. This is a genuine triumph. Decoherence explains the emergence of classicality. It explains why macroscopic objects do not exhibit quantum interference. It explains why the world looks classical even though it is fundamentally quantum. It identifies the physical mechanism, environmental entanglement, that makes quantum weirdness invisible at human scales. It does all of this without modifying the Schrödinger equation and without invoking anything mysterious. But here is what decoherence does not do. It does not explain why you see one specific outcome. After decoherence, the quantum state of the system plus environment is still a superposition. Both branches still exist. The electron is still in a superposition of spin up and spin down, correlated with different states of the environment. Decoherence has suppressed the interference between the branches. It has made them effectively independent, but it has not eliminated one of them. It has not selected a winner. Both branches are still there in the full quantum state. You just cannot see the other one from inside your branch. This is the crucial distinction that is so often blurred. Decoherence explains why you do not see interference. It does not explain why you see a particular result. It explains the disappearance of quantum effects at the macro scale. It does not explain the appearance of a single definite outcome. These are two different problems, and decoherence solves only the first. Think of it this way. Imagine you are in a maze with two paths, left and right. Decoherence is like a wall that drops down between the two paths after you pass the fork. Once the wall is in place, someone on the left path cannot see someone on the right path. The paths are effectively separate. But the wall does not explain why you ended up on the left path rather than the right one. It does not explain the selection. It only explains the separation. This is why decoherence, despite its importance, has not solved the measurement problem. It has clarified the problem immensely. It has shown that the classical world is not an independent realm governed by separate laws. It is an emergent pattern created by the entanglement of quantum systems with their environments. But the fundamental question, why does one outcome occur rather than another, remains untouched. In the many worlds interpretation, decoherence explains why the branches do not interfere, but both branches are equally real. In objective collapse theories, decoherence explains the appearance of classicality, but the actual collapse is caused by a separate mechanism. In pilot wave theory, decoherence explains why the empty branches of the wave function are invisible, but the particle was always in one branch. In Copenhagen, decoherence explains the practical emergence of classical behavior, but the fundamental status of collapse remains unaddressed. Every interpretation uses decoherence. None of them is completed by decoherence. The measurement problem survives. Now, let us push the question of observation into even more uncomfortable territory. Because so far, we have been talking about measurements as interactions between systems and detectors. We have been keeping the observer at arm's length, treating the physicist as a passive recorder who sits outside the quantum system and reads the results. But what happens when we put the observer inside the box? This is the thought experiment proposed by the Nobel laureate Eugene Wigner in 1961. It is called Wigner's Friend, and it takes the measurement problem from a technical puzzle to an existential confrontation. The setup is simple. Wigner has a friend. The friend is inside a sealed, perfectly isolated laboratory. Inside the lab, there is a quantum system, say a photon, that is in a superposition of horizontal and vertical polarization. The friend measures the photon. The friend sees a definite result. Let us say the friend sees horizontal. From the friend's perspective, the measurement is complete. The wave function has collapsed. The photon is horizontal. The friend writes this in a notebook. The friend has a definite experience of a definite outcome. The world inside the lab is classical, concrete, and settled. Now consider Wigner, standing outside the sealed lab. Wigner has not received any information from inside. The lab is perfectly isolated. From Wigner's perspective, the friend and the photon are both inside a closed quantum system. Wigner must describe the entire lab, including the friend, using the Schrödinger equation. And the equation says the system evolves into a superposition. One branch contains the friend seeing horizontal. The other branch contains the friend seeing vertical. The friend is in a superposition of two different experiences. From the friend's perspective, there is a single definite fact. From Wigner's perspective, there is no definite fact. The friend is in a superposition of seeing two different things. Both descriptions are generated by the same theory, and both are supposed to be correct. Who is right? Does the photon have a definite polarization, or does it not? Is the friend in a definite state or a superposition? This is not a question about information or knowledge. It is a question about the physical state of the world. And quantum mechanics gives two contradictory answers depending on where you stand. In the Copenhagen interpretation, this problem is technically sidestepped. Bohr would say that Wigner's perspective is the correct one until he opens the lab and interacts with the friend. At that point, the wave function collapses. But this just raises the old question again. What is it about Wigner opening the door that constitutes a measurement? Why does Wigner's act of looking collapse the superposition when the friend's act of looking apparently did not, at least from Wigner's viewpoint? In many worlds, the problem is dissolved by saying both branches are real. The friend sees horizontal in one branch and vertical in another. Wigner, when he opens the lab, branches into a version that meets the horizontal seeing friend and a version that meets the vertical seeing friend. There is no contradiction because there is no single outcome. But the price, as always, is the infinite multiverse. In pilot wave theory, the friend always sees a definite result because the particle always has a definite position. Wigner's description using a superposition is merely a reflection of his ignorance about the particle's actual position. But this requires accepting the non-local guiding equation and the fundamentally different ontology that comes with it. In objective collapse theories, the friend's measurement triggers a physical collapse inside the lab. By the time Wigner opens the door, the superposition has already been resolved by the spontaneous localization mechanism. But this requires the new physics of GRW or Penrose's gravitational collapse to be correct. And these have not been confirmed. So Wigner's friend does not add a new problem. It sharpens the old one. It shows that the measurement problem is not just about electrons and detectors. It is about people. It forces us to ask whether a conscious being inside a quantum system has a definite experience, or whether their experience is suspended in a superposition, waiting for an external observer to validate it. This would have remained a philosophical curiosity if not for a remarkable development in the last decade. Physicists figured out how to test it. In 2019, a team of researchers led by Massimiliano Proietti at Heriot-Watt University in Edinburgh constructed a real experiment inspired by an extended version of Wigner's friend developed by the physicist Czeslaw Bruckner. The experiment did not use a human friend, obviously. It used photons and optical equipment to simulate the structure of the thought experiment. One set of measurements played the role of the friend inside the lab. Another set played the role of Wigner outside. The key question was whether the results of the experiment were consistent with the existence of observer-independent facts. Bruckner had derived a set of mathematical inequalities, similar in spirit to Bell's inequalities, that must hold if certain assumptions are true. Those assumptions are roughly that measurements produce single definite outcomes that are the same for all observers, that a fact established by one observer is a fact for every observer, that the world has a single consistent history regardless of who is looking. These assumptions are the backbone of objective reality. They are the assumptions that allow us to do science, to build courts of law, to trust the testimony of witnesses. They are so fundamental that most people never even think to question them. The experiment violated the inequalities. The results were incompatible with the assumption that observer-independent facts exist. Let that settle for a moment. A real experiment, conducted in a real laboratory, published in a peer-reviewed journal, produced data that is inconsistent with the idea that the world has a single objective history. Not that our knowledge of the world is limited, not that our instruments are imprecise, but that the very concept of an objective fact, a fact that is true for everyone regardless of their perspective, may not apply to the quantum world. Now, this result comes with caveats. The experiment was performed with photons, not people. The violations depend on specific theoretical assumptions, and there is ongoing debate about exactly which assumptions are being tested. Different frameworks lead to different conclusions about what the violation means. Some physicists argue that the result rules out certain classes of hidden variable theories. Others argue it challenges the universality of quantum mechanics itself. The debate is far from settled, but the direction of the evidence is deeply unsettling. It suggests that the observer is not a passive recipient of pre-existing facts. It suggests that the act of observation plays a constitutive role, not in the mystical sense that your thoughts create reality, not in the New Age sense that consciousness is magic, but in the precise mathematical sense that the quantum formalism does not assign definite outcomes to events until those events are observed. And different observers, with different perspectives, may inhabit different factual frameworks that cannot be reconciled into a single God's eye view. This brings us to a concept that has been lurking in the background of this entire discussion. A concept that several modern physicists, most notably Carlo Rovelli, have placed at the center of their response to the measurement problem. The concept is called relational quantum mechanics. Rovelli's proposal, first articulated in 1996, is deceptively simple. He says that quantum states are not absolute properties of systems. They are relational properties. A quantum state describes a system relative to a specific observer. Different observers can assign different quantum states to the same system, and both assignments are correct. In Rovelli's framework, there is no universal wave function. There is no God's eye view. There is no single correct description of the state of the universe. There are only descriptions relative to particular physical systems. When the friend inside the lab measures the photon has a definite polarization relative to the friend. But relative to Wigner, standing outside, the photon does not have a definite polarization. There is no contradiction because there is no absolute state to contradict. This sounds like it solves the problem, but it does so by abandoning something enormous. It abandons the idea that the universe has a single objective state. It says that facts are not universal, they are perspective dependent. What is true for you may not be true for me, not because one of us is mistaken, but because truth itself is relational. This is not relativism in the casual, postmodern sense. It is a rigorous physical proposal grounded in the mathematical structure of quantum mechanics. But its implications are staggering. If Rovelli is right, then there is no fact of the matter about the state of the universe independent of a particular observer. The universe does not have properties, it has relationships. It does not contain things that are such and such. It contains things that are such and such relative to this or that. Every attempt to answer the question of what observation means in physics leads to the same disorienting conclusion. Observation is not what we thought it was. It is not a passive act of recording a pre-existing reality. It is entangled, in the most literal quantum mechanical sense, with the reality it reveals. When you observe an electron, you do not learn a fact that existed before you looked. You participate in the creation of a fact that did not exist until the interaction occurred. This is not mysticism. This is the content of the standard quantum formalism, taken seriously. The wave function does not assign a definite spin to the electron before measurement. It assigns probabilities. The definite result emerges at the moment of interaction. Before that moment, The question, what is the spin of this electron, does not have an answer. Not because we are ignorant, but because the answer does not yet exist. This forces a reckoning. We assume that the world is filled with objective facts, like a warehouse filled with boxes. We assumed our job as observers was to walk through the warehouse, open boxes, and catalog their contents. The contents were there before we opened the box. Our looking did not change them. Quantum mechanics says the warehouse might be empty until you open a box. And the act of opening does not reveal what was inside. It determines what is inside. The box, the contents, and your act of looking are all part of a single event that cannot be cleanly divided into observer and observed. The physicist John Archibald Wheeler captured this with his famous phrase, the participatory universe. He argued that we are not spectators in the cosmic drama. We are participants. Our measurements do not passively read the script. They help write it. Wheeler illustrated this with an analogy. He imagined a cosmic version of the game 20 Questions. In the normal game, the group picks a word, and the guesser asks yes or no questions to figure it out. The word exists before the questions are asked. But Wheeler imagined a version where no word is chosen in advance. Each person in the group answers the questions consistently with all previous answers, but without a predetermined target. The word is not discovered. It is created by the process of questioning, and it only becomes definite after the final answer pins it down. Wheeler believed the universe works the same way. It does not have a definite history until observers ask questions through measurements that force the history to become definite. This is not a fringe idea. Wheeler was one of the most respected physicists of the 20th century. He mentored Richard Feynman. He coined the term black hole. And at the end of his career, he concluded that the observer is not a footnote to the theory. The observer is the reason the theory produces a world. This is where the measurement problem reveals its true nature. It is not a technical glitch in an otherwise complete theory. It is a signal that the relationship between the observer and the observed is far more intimate than classical physics ever imagined. The measurement problem persists because the theory is trying to tell us something we do not want to hear. That the clean division between the world out there and the mind in here may not hold. That the solid, observer-independent, pre-existing reality we have built our entire civilization on may be an approximation, a useful fiction that works at human scales but breaks down when you look too closely. The question, what does it mean to observe, is not a question physics has answered. It is a question physics has opened, like a door into a room no one expected to find. And inside that room, the walls are not solid. The floor is not fixed. And the light only turns on when someone enters. We are not done. We have one more step to take, the darkest one. Because if observation is not passive, if facts are not objective, if reality does not exist independent of the act of looking at it, then we need to confront what that means. Not just for physics, but for existence itself. For what it means for something to be real, and for the terrifying possibility that the world you trust, the world you see and hear and feel, may only be there because you are there to see and hear and feel it. That is the dark answer. And it is waiting in the final stretch of this journey. We have arrived at the place where the road ends, not because there is nothing more to say, but because what remains to be said is the thing that changes everything. We have spent this entire journey mapping the measurement problem from every angle. We traced the crack in the foundation. We examined the contradictory rules. We walked through 4 radically different interpretations, each one a desperate attempt to hold reality together. We confronted the role of the observer and watched as experiments began to dismantle the very idea of objective facts. Now, we must face what all of this points to. Not a specific interpretation, not a technical resolution, but an implication so unsettling that most physicists would rather change the subject than follow it to its conclusion. The dark answer is not a theory. It is what remains when the theories run out of places to hide. Let us lay out the evidence one more time. Not to repeat ourselves, but to see the pattern that only becomes visible when all the pieces are on the table. The Schrödinger equation describes quantum systems evolving as superpositions of many possible states simultaneously. This evolution is smooth, deterministic, and linear. It never produces a single definite outcome. Every experiment ever performed produces exactly one definite outcome. The projection postulate, the rule that bridges this gap, is not derived from the theory. It is added by hand, and it depends on the concept of measurement, which the theory cannot define. Decoherence explains why macroscopic objects do not exhibit visible interference effects, but it does not explain why one specific outcome occurs rather than another. Both branches of the superposition survive after decoherence. The selection of a single result remains unexplained. 4 major interpretations attempt to resolve the problem. Copenhagen refuses to describe reality between measurements. Many worlds accepts all outcomes as equally real in parallel branches. Objective collapse modifies the fundamental equation with unproven new physics. Pilot wave restores definite trajectories at the cost of non-locality. None has been experimentally confirmed over the others. Recent experiments inspired by the Wigner's friend scenario have produced results inconsistent with the assumption that observer-independent facts exist. Now, look at the pattern. Every path we have taken leads to the same fork. At that fork, you must choose between 2 options. Either the quantum formalism is incomplete, and there is some deeper layer of reality that we have not yet discovered. A layer that produces definite outcomes through a mechanism we do not understand. Or the quantum formalism is complete, and the world simply does not have definite properties independent of observation. The first option preserves classical realism. It says the world is there whether you look or not. It says the moon has a definite position even when nobody is watching. It says facts are facts. But this option has a problem. Nearly a century of searching for the hidden layer has produced nothing. Bell's theorem proved that any hidden variable theory must be non-local, which means the hidden layer, if it exists, must violate one of the deepest principles of modern physics. And the experiments testing observer-independent facts are beginning to close even that door. The second option abandons classical realism. It says the world does not have definite properties prior to measurement. It says the moon might not be there when nobody is looking, at least not in the way you think. It says facts are not pre-existing features of the universe waiting to be discovered. They are events that emerge through the interaction between a system and an observer. This is the dark answer. Not that the universe is a simulation, not that consciousness creates reality through some mystical power, not that nothing is real. The dark answer is far more precise and far more disturbing than any of those. It is that the classical picture of reality, the picture where objects have definite properties at all times, and those properties exist independently of observation, may be fundamentally wrong. Not approximately wrong, the way Newtonian gravity is approximately wrong in the presence of strong gravitational fields. Fundamentally wrong. Wrong at the root. Wrong in a way that cannot be patched or corrected, but must be replaced with something else entirely. Let us be very clear about what this means and what it does not mean. It does not mean that you are hallucinating. It does not mean that the chair you are sitting in is imaginary. It does not mean that physical objects are mental constructs. The table is hard. The coffee is hot. The world pushes back when you push against it. These experiences are real. What may not be real is the story you tell about these experiences. The story that says the table was hard before you touched it, that the coffee was hot before you tasted it, that the world existed in its current state before you interacted with it. In the classical story, reality is like a photograph. The image exists on the paper whether or not anyone looks at it. The colors, the shapes, the details are all there, fixed and permanent. Your act of looking does not change the photograph. You are just a viewer. The image is the fact. In the quantum story, reality may be more like a conversation. A conversation does not exist before it happens. You cannot point to a shelf and say, the conversation is stored there. It has no independent existence apart from the participants. It comes into being through the interaction of two parties, and the content of the conversation depends on who is speaking, what questions are asked, and when they are asked. If you change the participants or the timing, you change the conversation. If a reality is a conversation rather than a photograph, then the measurement problem makes perfect sense. There is no mystery about why the Schrödinger equation does not produce definite outcomes, because definite outcomes are not properties of quantum systems in isolation. They are properties of interactions. The outcome is not in the electron, it is not in the detector, it is in the event of their meeting. Before the meeting, there is no outcome to predict. There is only a set of possibilities weighted by amplitudes. The meeting does not reveal a pre-existing fact. It generates a new one. This is the essence of what physicists call contextuality. The results of quantum measurements depend on the context in which they are performed. You cannot assign a definite value to a quantum property independent of the measurement that reveals it. This is not a limitation of our instruments, it is a theorem. The Cauchy-Specker theorem, proved in 1967, demonstrates mathematically that it is impossible to assign simultaneous definite values to all observables of a quantum system in a way that is consistent with the predictions of quantum mechanics. The properties simply are not there until the measurement context specifies which question is being asked. This is a direct assault on the most basic assumption of classical realism. We assumed that objects have properties. We assumed those properties are intrinsic. We assumed the electron has a spin, has a position, has a momentum, the way a ball has a color or a weight. The Cauchy-Specker theorem says this is wrong. The electron does not have a spin until a specific axis is chosen for measurement. And if you choose a different axis, you do not reveal a different pre-existing spin. You create a different fact. The implications of contextuality extend far beyond the laboratory. Think about what it means for the concept of existence. We normally use the word exist to mean is there regardless of whether anyone checks. The rock exists, the star exists, the atom exists. These things are part of the furniture of the universe. They have properties. Those properties are real. They would be real even if all humans disappeared tomorrow. But if contextuality is fundamental, then existence is not a standalone property. It is a relational one. A thing does not exist in the way we thought. It exists relative to something. An electron does not have a position. It has a position relative to this particular detector in this particular experimental arrangement at this particular moment. Change the arrangement and the position changes. Not because the electron moved, but because the fact itself is different. Carlo Rovelli has built an entire interpretation of quantum mechanics around this insight. In relational quantum mechanics, there is no absolute state of any system. Every quantum state is defined relative to another system. When your friend inside the lab measures the photon has a definite polarization relative to your friend. But relative to you, standing outside the sealed lab, the photon does not have a definite polarization, and both descriptions are correct. There is no higher authority, no cosmic referee who can declare one description right and the other wrong. This means that the universe does not have a single definite state. It has a web of relative states, a network of perspectives, each one internally consistent but not necessarily consistent with every other. Reality is not a monolith, it is a mosaic. And the pieces of the mosaic only exist where relationships exist. If this sounds abstract, consider the philosophical weight of what is being proposed. For 2,500 years, Western philosophy has been built on the assumption that there is an objective world out there. Plato believed in eternal forms that exist independent of any observer. Aristotle believed in substances with inherent properties. Descartes divided the world into mind and matter, but he never doubted that matter had definite properties. Kant argued that we cannot know things as they are in themselves, but he still believed that things in themselves exist. The entire tradition, from ancient Greece to modern science, rests on the conviction that there is a way the world is, and our job is to figure it out. Quantum mechanics may be telling us that this conviction is wrong, not that we are bad at figuring out the world, but that there is no way the world is independent of how we interact with it. The world does not have a fixed script. It improvises, and it improvises differently depending on who is asking the questions. Now, some physicists will push back against this conclusion. They will say that the experiments are ambiguous, that the interpretations are speculative, that we should wait for more data before making sweeping philosophical claims. And they are not wrong to urge caution. Science is a slow, careful process, and grand conclusions drawn from incomplete evidence have a long history of being embarrassingly wrong. But here is the problem with that caution. The measurement problem has been open since the Solvay Conference of 1927. It is not a new puzzle. It is not a gap that recent experiments have revealed. It has been staring at physics since the Solvay Conference of 1927, when Bohr and Einstein first locked horns over the meaning of the quantum formalism. In the nearly century since then, thousands of physicists have worked on it. Multiple Nobel Prizes have been awarded for work related to it. Entire subfields of physics and philosophy have been created to address it, and it remains unsolved. At some point, the persistence of the problem becomes data. If the measurement problem could be solved within the classical framework, within the assumption that reality is observer-independent, and that objects have definite properties at all times, someone would have solved it by now. The fact that no one has is not evidence of incompetence. It is evidence that the classical framework may not be the right one. The silence of the measurement problem is itself the loudest message. It is telling us that the assumptions we bring to the table, the assumptions of classical realism, may be exactly what is preventing us from seeing the answer. We keep asking, how does the definite world emerge from quantum superposition? And we keep failing to find the mechanism. Maybe the failure is the answer. Maybe the definite world does not emerge from quantum mechanics because it was never fundamental in the first place. Maybe the definite world is a user interface, an effective description that works at the human scale, a compressed representation of something far more complex and far less definite underneath. This does not mean the world is unknowable. It means the world is participatory. It means that the clean separation between subject and object, between the observer and the observed, between the mind in here and the world out there, may not hold at the deepest level. It means that reality is not a spectacle you watch from the audience. It is a dance, and you are one of the dancers. Your observations do not photograph the dance. They are part of the choreography. And here is the part that cuts deepest. If classical realism is wrong, if the world does not have definite properties independent of observation, then what does it mean for something to exist? We use the word exist so casually. The chair exists. The atom exists. The universe exists. But if existence requires a relational context, if properties only emerge through interactions, then existence is not a binary state. It is not a switch that is either on or off. It is a process, a continuous, dynamic, context-dependent process that unfolds through the network of relationships that constitutes physical reality. This is not nihilism. This is not a claim that nothing is real. It is a claim that reality is richer, stranger, and more deeply interconnected than we imagined. Things do not exist in isolation. They exist in relation. And the relations are not secondary features of a world made of independent objects. The relations may be the primary reality. The objects may be the secondary features. The nodes of the network may be less real than the connections between them. Some physicists find this liberating. Ravelli has written beautifully about the relational nature of reality, comparing it to the way meaning arises in language, not from individual words in isolation, but from the relationships between words in context. Others find it terrifying, because it means there is no fixed ground to stand on, no ultimate truth that exists regardless of perspective, no God's eye view from which the universe can be described once and for all. But perhaps the most honest response is humility. The measurement problem has taught us that our intuitions about reality are not reliable at the quantum scale. The concepts we use to navigate the macroscopic world, definite position, definite momentum, definite state, are not built into the fundamental physics. They emerge from it through a process we do not fully understand, in a way that depends on interactions we are only beginning to map. The dark answer is not a specific theory. It is a recognition that the measurement problem is not a puzzle we have failed to solve. It may be a message we have failed to hear. And the message is this: the universe does not owe you a reality that exists independent of your participation in it. The universe does not promise that things have definite properties when no one is checking. The universe does not guarantee that the facts you observe are the same facts another observer would observe. The universe does not assure you that the ground beneath your feet is solid all the way down. What the universe does offer is consistency. Within your branch, within your perspective, within your relational context, the laws of physics hold, the predictions work, the probabilities match, the coffee cup falls when you drop it. Every time. The universe is not chaotic. It is not arbitrary. It follows rules with extraordinary fidelity. But those rules may not describe a world that exists independently of the observations that probe it. They may describe the structure of the observations themselves. Think about what this means for you, personally right now. You're sitting somewhere, hearing these words, experiencing a world that feels solid and definite and utterly real. And it is real. Your experience is genuine. Your perceptions are valid. The world pushes back against you with the same reliable force it always has. But the thing you assumed was underneath that experience. The thing you assumed was the source of that experience. The objective, observer-independent, pre-existing physical world may not be there. Not in the way you thought. What may be there instead is a vast quantum network of possibilities. A web of potential facts that only become actual facts when something interacts with something else. And you are part of that web. Not a spectator looking in from outside. A thread woven into the fabric. When you observe, you do not read the fabric. You tighten a knot. You make a connection. You participate in the creation of a fact that did not exist a moment ago. The measurement problem asked a simple question. Why do we see definite outcomes in a world governed by superposition? And after 100 years, the deepest answer physics can offer is this. Maybe we see definite outcomes because seeing is what creates them. Maybe the outcomes are not features of the world that exist before observation. Maybe they are features of the relationship between the world and the observer. Maybe the sharp, classical, definite reality you trust so completely is not the foundation. Maybe it is the surface. And underneath that surface, there is something far more fluid, far more entangled, far more dependent on the act of looking than you ever wanted to believe. This is not a comfortable conclusion. It offers no easy reassurance. It does not tell you that everything is fine and the physicists will sort it out eventually. It tells you that the physicists have been trying to sort it out for nearly a century, and the problem keeps pointing in the same direction. Toward the dissolution of classical realism. Toward a world where existence is participatory. Toward a universe that does not sit still and wait for you to describe it, but shifts and shimmers and becomes in response to your questions. The measurement problem is not a failure of quantum mechanics. It may be quantum mechanics trying to tell us the most important thing it knows. That reality is not a thing, it is an event, it is not a noun, it is a verb. It does not sit there. It happens. And it happens, at least in part, because you were there to make it happen. You opened your eyes this morning and saw a room. The walls were solid. The light was steady. Everything was exactly where you left it. And you took that as evidence that the world is real, that it is permanent, that it exists, whether you look at it or not. But consider the possibility that what you actually witnessed was something far more remarkable. You witnessed a world assembling itself in the act of being observed. You witnessed quantum superpositions resolving into definite facts at the precise moment your senses made contact. You witnessed the universe making itself real for you, in real time, one interaction at a time. You did not see a world that was already there. You saw a world that was becoming. And the becoming was not separate from your seeing. They were the same event. This is the dark answer. Not that reality is an illusion, but that reality is an achievement. An ongoing, collaborative, moment-by-moment achievement that requires participation. That requires interaction. That requires something, somewhere, to ask a question of the quantum fog and receive an answer. And the silence that surrounds this answer, the silence of the measurement problem, the silence of physics unable to explain its own most basic process, that silence is not emptiness. It is the sound of a universe that refuses to be pinned down, that refuses to exist in a single definite way for all observers at all times, that insists on being a partner in the act of its own creation. The measurement problem has a dark answer. The answer is that the world may not be there when you are not looking. And the only reason it appears to be there is that you have never, not once in your entire life, stopped looking long enough to find out.